Well, this is the beginning of chapter 22, section 1. And what we're going to do is move from talking about static electricity to electrical currents. And this is actually a pretty important jump because, for the most part, what makes, let me turn that up a little bit, um, what makes electricity useful is the fact that we can cause it to flow from one place to another. There are applications for static electricity, don't get me wrong, but for the most part, what we are interested in is what happens when electricity flows. So, for instance, I have a light bulb which is not on, but this light bulb works because electricity flows in, goes through the bulb, and then comes out the other end. Actually, that's not quite true, but it's close enough. And it warms up a filament inside of here. Other bulbs work different. This is an old-fashioned light bulb. But what we have is electricity flowing. In almost every application that we would use, you're going to have electricity flowing. So let me give some definitions. Electrical current is going to be defined as a flow of charged particles. Notice the word there. It's a flow. We think of electricity almost like Benjamin Franklin did as a fluid. It's something that flows like a river would flow from one place to the other. The charged particles are usually electrons. Again, usually there are times where other charged particles are moving. So I want to take you back to something. If I had a plate that was charged positive and another plate that was charged negative, and I'm going to do something a little different. I'm going to put a negative here, a little electron. If I said I'm going to put an electron right here, you should know what's going to happen. It's going to go like this. There is actually a voltage across here because there's an electric field and there's a certain distance. If I was to take and hook up a conductor, a piece of, say, copper wire, from here to here, when I touch it, these electrons will flow until we finally have no charge. No charge on the negative plate, or we run out of electrons on one of the plates, or we run out of positive charges up here. By the way, charge is like mass. It's conserved. You don't ever lose or gain charges. They can combine together and become neutralized. All right. Now, the problem with this is that if this was a capacitor, which we've already talked about, if I put this wire here, the discharge, the flow of electricity would be almost instantaneous. Electrons will flow through wires at about 1/10 the speed of light. This happens almost instantaneous. In a large sense, if you watch a lightning bolt, the clouds in the earth are a capacitor. You can have a huge amount of electricity, but it's over in a couple of seconds. And as a result, it doesn't become super useful for us. And in order to make electricity useful, we have to find a way of maintaining an electric current. We have to have a way of making sure that electric current flows. Let me give you an analogy. And this is a very common analogy. My dad was an electrical engineer, and he used to use this analogy for me to help understand. So imagine you have a lake. And by the way, it could be a big lake, it doesn't matter. And you had a river that's flowing out of that lake, and it's going downhill and then out. And somebody takes and puts a water wheel here. Obviously, kind of a weird drawing, but a water wheel, something that's going to spin around. As long as water is flowing, this water wheel will spin. When will the water wheel stop? Well, it'll stop when there's no more water in the lake. And at that point, this is no good. In a capacitor, that will happen instantaneously. But let's say we wanted that water wheel to keep flowing. I could put another lake down here, the same size, and then I could put, let's say you're at Disneyland and you want this to go on forever. I could take and put a pump right here. And that pump could take the water that accumulates in the bottom, pump it at the top, and this water wheel would keep spinning forever. And you say, but it takes as much energy to pump it back up. That's true. But if I want that water wheel to keep spinning, I need to somehow keep replenishing the water. Now, if you think of this as the negative and this as the positive, then this must somehow transfer and push the electrons back to where they did not want to go. Going uphill is the opposite direction. And that right here, an electron pump, has a name. It's called a battery or a generator. So let me talk just a little bit about a battery. Here's how you make a battery. A battery is two dissimilar metals. So that would be any metal like copper and zinc, or silver and carbon, a carbon rod. It could be any two dissimilar metals. Carbon is not really a metal, but it gets used a lot. And then some sort of a fluid or substance that causes them to lose electrons. And so a salt or acid solution. The man who figured this out, the name that comes is Alessandro Volta. And my guess is you can figure out where we get the word for volt from. It's from his name, Alessandro Volta. And Alessandro Volta discovered this property. In fact, he made what was called a voltaic stack. And I'll describe that for you in a minute. If you were in class, I would have you build a battery. There's a number of ways to build a battery. Here's how I would do it. I would take some water, put a little bit of acid in there. It could be vinegar, but acid. Take a piece of copper and a piece of zinc. And believe it or not, if you connect that up, you will get about 1 volt. The reason it's working is this. The acid causes this to lose electrons. It begins to react with the copper. And as a result, you get a charge on the copper and you get a charge on the zinc. The charge is not exactly the same, so there's a dissimilar charge. And even though they both are the same sign, and I want to be careful because this is being filmed on YouTube. I believe it's a positive charge that they both take because they're losing electrons. One is more positive than the other, and because of that, electricity will flow. Alessandro Volta made what is called a voltaic stack. You can make one yourself, but before we do that, if you took a lemon, a lot of you know about this, take a penny and take a galvanized nail and put that into the lemon and measure it, it will be about 1 volt. All right. There's another important man called Galvani at this point, but in the interest of time, if we want, you can look him up. He actually discovered that the human body took frog legs and found out that you could cause a frog's legs to twitch with electricity, and that was an important discovery. Alessandro Volta made what he called a voltaic stack, a kind of a forerunner of a battery. And what he did was he took pieces of copper, and then he put a piece of like cloth soaked in acid or acid or salt water, and then he put a piece of zinc, and then a piece of this would be your cardboard or cloth. So it's copper, zinc, another piece of copper. And what he discovered is the more of these he did, the higher the voltage was. And he was able to create large voltages. All right. Now, let me talk about what you guys will be doing with this. Let me erase over here. In fact, I'm going to erase all of this. It's a shame that we can't build a battery. At the end, if we don't cut out, I'm going to show you some batteries. Otherwise, I'll do that right at the beginning. The unit of current, when we talk about electrical current, the unit is the amp, and the symbol in the equation is I. Voltage, you already know. Voltage, the unit is the volt, and the symbol is V. It's one of the rare ones where it's the same. If you see V in an equation, it means voltage. And let me throw back something from before, power. The unit is the watt, and the symbol is a capital P. So current's a little odd. You would think that would be a C, but we already have that for Coulomb. All right? Let's start with this. 1 amp is actually a flow of electricity. It is 1 Coulomb of flow per second. So the unit of the amp is actually a Coulomb per second. And if I said I have something that's 20 amps, that's 20 Coulombs flowing every second. Remember, with current, then, current is joules per second. Voltage is joules per Coulomb. Coulombs per second. And power is joules every second. And that causes there to be a very interesting equation. Power is voltage times current. And that's because power is joules per second, voltage is joules per Coulomb, and current is coulombs per second. And we get the exact same unit. That's our first equation when we start working with electricity, is that power is voltage times current. By the way, if you say that something has, in fact, this light bulb right here is a 100 watt light bulb. What does that mean? 100 watts means 100 joules every second. Right? But if I had a 100 watt light bulb and I had 120 volts, which by the way is what your household voltage is, I can actually divide that, and this will be some of the problems that you do, and you will find that you have 0.83 amps is the amount of current. Remember, this is joules per second divided by joules per Coulomb, and when you redo that, you're going to get joules per second times coulombs per joule, 0.38 coulombs every single second. So it's very interesting. If you, just so you know, around your home, you'll have either 120 or 240, sometimes 110 or 220, but it goes up to 120 and down to 120 and 240. And if you look at something and it tells you what the rating is, that tells you how much joules per second, but unless you know the voltage or the current, you aren't sure what's going to happen. So I could have 100 watts. If it was only 12 volts, then I would end up with 8.3 amps that would be flowing through that. So we have this equation, and you're going to work with that. P equals voltage. They do IV in your book, but it doesn't matter. Remember, too, that power is power times time is work. And in this case, work is energy, and energy will be in joules. So they're going to give you a couple of problems that are like that as well. Let me quickly, before I finish, show you a battery. This, by the way, is called my Leyden jar. This is a capacitor. This is metal, and in between is a plastic container. If I put these together and I hold on to this and I charge this one, I somehow put electrons on here. I would have done it with my big Van de Graaff generator and then charged it up. If I'm holding this and I touch it, electricity is going to flow through me right across my heart and back over to here. And fortunately, this is designed so it puts out such a low amount of current, it doesn't stop my heart. And this is where we would take, and everybody would hold hands around the room, and then one person would touch it, and the electricity would flow through all of us. This is a battery. It's an old-fashioned battery. We used to use huge batteries for lanterns. Now we have such better technology. But I want you to just take a look at this. I'll bring it up a little closer. This is zinc. That is zinc metal. On the inside is a carbon rod. We could use copper there. And in between it is a paste. And that paste is an acidic paste. One thing I forgot to mention with the battery is you have to ask how long will a battery work? Well, it'll work until the metals are gone or the acid is used up. So this was called a dry cell. This is also a dry cell, but this is one where I have 3 of them. I don't know if you can see this or not. There is a wire that goes from the zinc to the center, from the zinc to the other center, and there used to be 4 of them here. Each one of these are 1.5 volts, and put them together and it got a 6-volt battery. These just come in a little package. One of them got lost over the years. A wet cell, if you take a battery, like just a typical, what you guys would be used to, say a D battery, if you cut that in half, you will find that you have metal here. By the way, I don't recommend this. I've done it once and it's actually fairly dangerous. This is zinc. This is copper. And it's actually a rod that goes from the bottom up. And the one side is copper. I think it's this way. It's the copper top battery. This is copper. This is zinc. And they would put an acid liquid inside of here. When I was a kid, I found a battery that had been run over on the street, and I was just 9 or 10 years old, and I picked it up, put it in my pocket, because I thought it was pretty cool, this smashed battery, and a few minutes later, my leg is burning. It's burning because the acid is leaking out, and it's actually fairly strong acid. So anyways, you're going to do some problems for me. The problems you're going to do are on page... Well, they're at the end. I don't have the page. They're the practice problems. And I will put it up. I believe it's 1 through 5. It's real simple. Problem 2, we're going to do all of them. Problem 2, the answer is 24 watts. And problem 4, the answer is 252 joules. And go ahead and try those for me. I'm going to put up one more video, and that will finish us for the week of 18 through 25. All right. Go ahead and read the chapter as well, and the second video will be coming up real soon.